Good afternoon. Thank you so much for inviting me, and just been such a wonderful time. So thank you for wonderful hospitality. The coalitions know how to host people. So thank you so much. And a few disclaimers. So I am not a mathematician, so I'm an engineer. So I'm not very rigorous. So let me know, just be forgiving. Two, I'm not trained as a dynamical systemist or control person. So again, I'm still a student, but today I'm going to tell you about how to control dynamical system that's nonlinear using Koopman. So take it with a grain of salt. I don't know what I'm talking about, but again, let me know afterwards if I'm doing something wrong. And today, this work actually done, I want to say my PhD student has been really the one who's, comes with good ideas. And again, he's going to be on the market, or not again, but he's going to be on the market in a few months. And if you have any open positions in Michigan or remote, let me know. He's a really good student, really bright. But I'm going to tell you about how we are acoustically control microbubbles using Koopman quadratic regulator, LQR. I can't say that well. I'll say LQR. All right. There you go. So, and by the way, I'm going to say this is not quite a killer app, but hopefully it gives life later on. So, but it's still an app, okay? So meet the microbubble, bubbles everywhere. The specific bubble that we would like to ultimately work with is a bubble that's coated and it's tiny. It's like ranges from half microns to 8 or 10. 10 actually, 10 might be an old number now. It may be 8 or 5 microns. Now, if you can't imagine what that looks like, a piece of hair, 50 microns, like the diameter of your hair. So if you kind of a 10th or even 1% of your hair diameter, that's what the bubbles sizes are. Now, why so small? Mainly because they're fused, and so they inject these bubbles into into your bloodstream, and so they have to be small enough to get through some of the smallest vessels you have, actually in the lung, or as well as doesn't kill you, because when you inject too much bubbles, you actually can die. That's why the nurse, when they push it out, so not to kill you as well, and that's why they're small. And typically they have a coating, so it could be lipid, protein, polymer. The coating actually helps it persist longer in your body, so it doesn't dissolve right away. So that's what the coating is for. And then there's a inert gas in there. Now, I will tell you next. You're wondering why do we care about these bubbles? Why their application are. All right. So I'm going to tell you about a few applications. This one actually is being clinically practiced for 20 years. And it's ultrasound enhancement agent. Okay. So here I have a picture of a rabbit kidney. So someone else is using rabbit insertion. I think it was Jeff, something like that. But anyway, so on the left, you have a picture, an ultrasound picture before the arrival of the bubbles. So they inject bubble into the rabbit. And then on the right, the B, you see the lighten of the kidney, and that's after the bubble has arrived. So you can see that before and after, it really enhances the imaging. And how does that work? You might wonder, not magical. It actually, because of nonlinearity bubbles, so it responds to ultrasound in a different frequency than what you're supplying it, and much more pronounced than your tissue. And so it really magnifies it in that way, okay? And so the second application, and the other ones you see from here are more like kind of preclinical and still very much just in research mode, okay? And this is where it helps coax the cell from opening up to allow drugs to enter in, or whatever else you want to deliver to the cell. So it does it through a few ways. So it does through interacting with surrounding fluid, mostly blood or whatever you have in that, to kind of coax the cell from opening up. Again, I'm not a biologist, so correct me if I'm saying something wrong. Specifically. And then it actually the oscillation, the contraction and expansion of the cell can actually physically interact with the cell walls, and that can actually coax it open. And then lastly, there's inertial cavitation, it like just bursts and ruptures, and that can create an opening and so forth. So that's one way of using it. This is actually for cancer treatment, and these are none of my videos. They're from YouTube, so credit to them. Let me how to play it. How to do this. So this is for in non-invasive treatment of cancer. There's little cancer cell right here in the bubbles, and they cause them to rupture. And because the pressure it causes from rupture, it apparently destroys some of the cells. So then it's a way to destroy tumor cells without really having to do radiation and so forth. So again, these are very much initial preclinical and very kind of far away from actually being practiced, but that's there. Next, I want to show you how the bubble behaves. Okay. Again, this is not my video. You can see someone else's bit, but it's a good illustration. But I want you to kind of notice one thing, or two things. So bubble, you think of it spherical, right? Think about spherical. Okay. There's actually, so someone's going to drive the bubble with ultrasound and see how it oscillates. You notice two things. First thing is that the spherical phase is very brief. It's like you almost will miss it if you don't look carefully. Okay, two, once the spherical phase is gone, you see the non-spherical oscillations. And there will be a very, again, brief, stable oscillation. And then it's like goes a little berserk with jetting and so forth. Okay, so those two things. So the spherical phase is brief and the stable oscillation phase is brief, and then it goes berserk. Okay? So, and it's a long video. I won't play all of it. Has fun music. Keeps you awake. I know someone's falling asleep here. But again, I wish actually I'm building my own bubble trapping thing in my lab, so it might help my colleague do experiments, but we're not quite there yet. And the bubble is against a glass substrate. Keep it there. So you have the bubble. See how it's already gone, you lost it, and then it does crazy things like jetting. Have a bulb, so being pinging that. It goes on for a little while. Actually, this is the point where I've got my point. It's like 2 or 3 minutes, so I don't want to spend that watching it. But you can, it's on YouTube. I'll send your link. So okay, so those applications, I kind of want to give you an idea of what we are trying to do with the bubble. Right, there's two things basically we want to do with it. We want it to oscillate in a stable oscillation without going crazy. You see how if you don't do anything, it goes crazy. So how do we keep it in a stable oscillation? And two, how do we make it rupture? So there's some applications we want it to burst, right? So how do we make it burst? So we sometimes for some applications like the ultrasound as well as the sonoporation, but the opening of the cell walls, you want more stable oscillation sometimes, right? And sometimes you want to rupture it. So you want to be able to do both control well, not just kind of like do something and hope it works. And actually that's how they do it now in practice. What they do is, well, if I want stable oscillation, I want low amplitude. Makes sense. And if I want like rupture, I go high amplitude on my driving force. It makes sense, but it's not concise, so not exactly. Actually, what we'll show at the end is that you could sometimes cause it to rupture even at low amplitude, depending on if you're driving at a specific frequency. And you guys can go high amplitude. If you're the right frequency, it can still be stable. So we are trying to figure this out using Koopman. So 2 goals. All right. I made this figure actually in the previous one to using Copilot, because that's what we have. It's an awful job because I'm not an artist. But this is a roadmap, and you can see spell measurement with 2 N's instead of M. Funny, but I didn't catch it for a long time, so actually AI couldn't catch it because M looks like a 2 N's. But anyway, anyway, the point is that we have a long way to go. I'm right here. I'm at like uncoded. So right now we're looking at an uncoded bubble in water, right? Nothing like the real case. Real case of coded bubble when it's in blood, right? And then you have surrounding tissues in your. So we're a long way, but and also we don't see the bubble when it's in your body. You can't see how it oscillates, right? You can't. So we want to remove the exact state measurement and do observables, which is the acoustic echo the bubble releases. We can measure that. So we want to use the acoustic echo that we can capture to drive and controllable. That's our ultimate goal. We're not there yet. Actually, my student's gonna do the state estimation and removal of the exact state measurement using Koopman as well. Okay. All right. So I'm gonna start by giving you brief background on bubbles and then a quick overview on my Koopman's framework, show some little fun results. Okay, I think it's fun, but okay, you can tell me later. All right, so I don't know if you know this, but Laura Rayleigh, the Rayleigh's Taylor instability Rayleigh, 2 years before he died, he derived a spherical bubble model. So it's known as a Rayleigh-Perset model. Perset kind of improved it later on, but Rayleigh was the one who first derived it 2 years before he died. And so anyway, so he derived purely a spherical. Again, that's easiest. And you see how brief that spherical phase was, right? It's like this barely little bit and it becomes like crazy non-spherical. So people have gone over the years, have improved on it, and plus that's one of the people who did improve on it. And the way that they model, at least on the ODE manner, is to add additional terms that govern the non-sphericalness. So you have how's the laser? Here you go. Is this laser? So you have the spherical term and you have the additional non-spherical terms. Let me go and click through. Which are basically the asymmetric spherical harmonics. Okay, and so you plug it through the conservative energy and so forth. You get ODEs. You get an ODE for the spherical mode, and you get an ODE for the non-spherical modes. Okay, so you get the amplitude because those are known. So the amplitude is what you get an ODE for. Spherical mode, highly nonlinear. I wrote this one so you can see. It's like nonlinear. The key thing in here is very weird, is that the control input ultrasound enters only through the spherical mode in this formulation. And then it indirectly through the spherical mode enters and controls the non-spherical through the coefficients here and the parametric. This is actually nothing but a spring mass damper, but nonlinear, right? You have a damping term that's function of radius, and you have a subsurface term function of radius. So your control input does not directly affect this; it's implicit through the radius. So, but our goal actually, especially when you want to cause stable oscillations of the non-sphericalness, we had to go cause it through the radial version and then have that do that. Okay. So that actually made us force us to use an observable framework to do this. So with that, that's the framework. And how are we doing time here? How are we doing time? Who's trying time? My phone. Okay, thank you. So just to help you get to know this bubble model better, the way that we train the data to get Koopman and I worked, my PhD student made the kind of blob. If that's distracting to you, don't look at it. But the spherical modes, if you make the phase portrait, on the x-axis, we have the radius and radial velocity. We compress it initially, no forcing, and let it go, and then it kind of spirals in. So, it samples phase space really well. It's one thing we learned, that you want to get a good approximation of Koopman function. Eigenvalues, you want to sample your phase space well. So that's a good job. And then if you look at the non-spherical modes, the A's and how they behave. One thing I want to point out, I didn't show you before, but this damping term is proportional to the radial velocity divided by radius, and the stiffness term is proportional to inverse. Okay, not important here, but this term is more important. It's kind of weird, this model, and I don't like it, but we're gonna move away from it and do coding soon. But when the bubble is when the radial mode is 0, so radial mode velocity is 0, so r dot is 0, you have 0 damping. Yeah, so that means that if your bubble is at equilibrium radius, your shape modes keep ringing, even though the radial modes are stationary. So it's really non-physical, but it is what it is. And it will affect our result a little bit. But I think if you add viscosity to your non-spherical modes, it will change that. But I don't know how much it will change it until we do it. So anyway, so this is the training data for our. You see, this is alpha 2 sites, which should be A2, but so it has initial bounce, and then it just rings indefinitely because it's missing the viscosity. Because once the bubble radius becomes its equilibrium radius, this term goes to 0. But the non-free mode is still ringing. So non-physical, but this is what we got. Okay, and we're not staying here. We're moving on to a more sophisticated model. And this is an easy model to start with. So anyway, I do use Cindy. Not because of my name, my PhD student just picked it, and he just told me that's what he's using. So I said, okay. I mean, so, no, yeah. And I get a joke a lot. Like, do you use Cindy because your name is Cindy? No, but my PhD student just picked it. So anyway, I mean, you can use anything. You can use EDMD and just something to approximate Koopman eigenfunction. So I'll click through that because Stefan talked about it. So you have your X, which is states, right? And you have your series, and I use monomials because it's simple enough. And then we assume your Koopman function can be written as a linear combination of the functions, and you compute a numeric derivative, and you go through that, and least squares issue. You can do sparsity if you want, so forth. We actually, there's no why too, because we follow Kaiser's paper, and so she does that. So my student's following her formulation. Okay, so that's how you get eigenfunctions. The control part, you start with this control affine system, and I think Jeff talked about how you kind of do the chain rule and apply the system. So you've seen that before. So if you look at the companion system for the Koopman eigenfunctions, it's that. So gradient psi times your b, whatever b happens to be, and gradient psi is your array of eigenfunctions that you're picking. You have eigenvalues along the matrix and so forth. Okay, so the LQR part really is that instead of controlling your x, right, which is nonlinear, you're controlling your eigenfunctions are linear. So you just use LQR, right? And Igor said he talked about it 1980s or 90s. Sorry, not that old. 90s. Okay, anyway, so there you go. 90s, right? Anyway, this thing's not working. There you go. So yeah, so all it is that you're applying linear LQR, but to the Koopman. So you have a Koopman target instead of a target for X, and how you get the Koopman target you plug in X target, and so you get different target. And it works really well. Actually, we can really get away. Actually, and what we find is that for a long time we were struggling to control it because we were using Koopman eigenfunctions that were not that were not accurate, that had high residuals. And so to Paula's point, like, so it took us a while to figure out, oh, we gotta pick the right Koopman eigenfunctions to control, because we picked the wrong ones, and the ones with high error, they don't work well. So then we picked one with low error and it worked magic for control. So with that, that's our QR. Because I said we need to control through observables ultimately for us. And so we do the same for work, but we control. So you have G with your control with observable. You have things that you measure, not the state necessarily. I call it G. And so same thing, you go through your dictionary, and then that's one thing I assume, now tell me if it's wrong, but tell me later, that somehow you can find Koopman functions that can be written in close approximation in terms of G of X, right? And so then same thing. Now what happens is that you have your Koopman as function of your G target. That way you can have a target that's an observable target and not necessarily a state target. So you can do that, and then everything goes to the same thing. So same LQR and that, and you're done. And so that's our theory. How much time do I have? Really? Okay. I'm going way faster. Okay. All right. I guess I'll finish early. I think. I don't know, maybe not. Okay. I haven't run this before, so I don't know how long this takes. So here we go. So again, reminder, this is my training data to get my Koopman eigenfunctions. I have my radial modes kind of spiral in. I have my forever ringing non-spherical modes, and those are the damping and the stiffness that came from the radial mode to the non-spherical modes. Okay. So the first goal, remember I told you there are two goals, right? I wanted, sometimes for some applications, I wanted to kind of ring in a stable. Now, right, if I don't do anything, it can only really ring at the equilibrium radius of the bubble, the R0, that's what's happy at. But what I want to do is to drive to ring at whatever frequency I want. Okay, so, and ideally to be a different frequency than what the driving frequency is, so that I can really capture that echo. All right, so that's my first goal. Again, reminder of the ODE that we're working with. It's a nonlinear spring mass damper model with the stiffness and damping come from the radial terms. And this is actually quite easy. So if I wanted to ring at whatever frequency, I just set C to 0 and have to set stiffness to whatever stiffness I want, basically. And this is actually quite easy. So I just make R dot 0. So our target for this problem would be R dot is 0 and R is whatever R we want to drive it to. And you can see right here, so I have R to a fixed R, and that will give me, and I can raise and lower the level of R to give me whatever frequency I want with the shape modes. Okay, so it works quite well, and actually this is quite an easy objective to achieve. So this point is not working. So this is the control input I got out of the Koopman LQR, and you can see the resulting shape non-spherical modes, and this is prescribed by us in our target, right? And so it does like that forever until I change my control input. And you can see how thin the Fourier transform is. So it's really, really bright on. Okay. Okay. Now the harder target, I think, is to, well, not harder, but I think my PhD student actually, he gets all the credit for coming up with a really clever way of getting a bigger picture than we thought we were going to get. So you can make it burst. Okay, you can actually make it burst by driving, because it wants to get into the really funky jetting. If you remember from the video, it likes that. So you can easily get it to do funky things. But the question is, if you want it to burst when you want it, and at what control input, like, because you don't want to drive it so hard where you're actually hurting the patient with ultrasound, right? But you don't want to drive it so light where it's actually, or maybe you're not causing to burst. Okay, so we can I'll get there. So what my student came up with is actually come up with the stability diagram for a bubble. So he actually converted the non-spherical shape modes into Hill's equation and do some fairly nonlinear transform. And so once we have Hill's equation, what we do is we assume that we have periodic radius and radial velocity, and then we put it into our, if this is periodic, and this is periodic, and this is periodic, and this is periodic, and then we can use bouquet theory, generate a instability diagram. And this is where I said the knowledge, being used by clinician is if I wanted to oscillate, indefinitely, I do slow amplitude. If I want to burst, I do high amplitude. But you see here, okay, if you can see the colors, you have purple or blue is stable. So you have stability, of course, at some low frequencies. A low amplitude. So B here, by the way, is amplitude, and omega is a frequency, right? And so at low amplitude, yes, you get that intuition is correct, but at these spikes, you can cause ball to rupture, even at low amplitudes. You see that? So the yellow is unstable. So you can see yellow kind of comes down. And why? Because you're driving it at the resonant frequency of the non-spherical modes. And so whatever mode that you're hitting, actually, this is the second mode. So I actually showed an example of this right here. So you're actually driving the second mode to go berserk. But you can also, where you see here the blue, you can go pretty high up if you stay low enough frequency. You can high up in amplitude and still have stable oscillation. So there's a lot more we can understand when we do analysis like this than just kind of regular clinical intuition of just blanket low amplitude or blanket high amplitude. Okay, and so what I will show you next is that we drive the spherical modes to follow a oscillation right here. So again, low amplitude, but still rupture. And then we actually drive up here. And actually, it's in the yellow region. So it still ruptures, but we're actually driving at a higher amplitude. So you see those very funky things. Okay. All right. So with that, so this is the linear regime where you're driving at a very low amplitude, but you can cause rupture. So here is my control input. So U, and this came from the Koopman LQR. Gave us that. So on the x-axis I have tau, and y I have U. And then here is the target that I gave it, right? So I want, and actually see how, by the way, I don't have a legend here, but the blue is the target and the red is what the system is doing. So Koopman LQR worked really well to drive my bubble to follow that path. And by the way, in my notation, 1 is the equilibrium radius, so it's way above the equilibrium radius. So this is not, it's not happy being there, but we are forcing it to be there, right? And my alpha is my alpha 2 against my A2. It's my second non-spherical mode. And you see it's going berserk, and it's growing. And that's because we're driving at the resonant frequency that it wants to be. And so it's really happy and going crazy. But you see the alpha A3 is one mole higher, and that's stable. And so you can drive low amplitude so that's obvious, I guess. And then the nonlinear regime is that where we then here you have actually high, so we have, again, same thing. We have time and you have input, and then you have your time and then radius. So again, actually here, you're actually driving it at a nonlinear. It's hard to tell actually nonlinear. Typically, you see this a little sharper than the top. So I don't know why it's too bad. No, you know what? We're driving it to be sinusoidal. So you don't quite see that actually here. But you can see in control inputs, it's much more nonlinear. And then here is the second mode. It's doing more crazy stuff, and you can see the video right here. Actually, it needs to loop over. Kind of get stuck, but there you go. So it's kind of going up and down, and then eventually burst. So those there we've driven it to go unstable using a high amplitude, which is what people should already know. But just to show you that we can do that as well. And lastly, I guess just to show another fun example that we can drive it to implode. So since I have time, we can watch it. And that's using a linear combination of the two different frequencies. It's going. Suspense. Oh. 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 I have time, right? Okay. Oh, there we go. Yeah, I did it. Okay. So that's to say, that's my time. Thank you. Is that me? Oh, that's me. Okay. So that's to say, now with the Koopman LQR, what can we do? We can create maps like this. What does this say? This is time to blow up as a function of frequency and amplitude, and how much energy we're using to make it blow up, a function of frequency energy. And so with this information in mind, I can generate for real bubbles and with code bubbles. So I can say is, when do you want bubble to blow up? Tell me. And then you can say, you can pick a time and then I can give you the frequency and to do it. So you can precisely make it rupture whenever you want, of course, with good control. And something too, like if you ask like, okay, well, if I have a constraint on how much energy I can put into the patient, right? I don't want to kill the patient. Here's my limit, and I can tell you what frequency and what amplitude you should drive it, or below that where you're safe. So this is what we're able to achieve. With that, I'll conclude. So we're really able to have very good control of our microbubble, which is highly linear. And sorry, I don't know. That's been a mystery to me why that's good. But anyway, and be able to drive it really with good control to do two things. I'm gonna go over that because anyway. And thank you for Insight for finding this work. Okay.